Jnanam Paramam Dheyam. Knowledge is supreme.
In the last lecture, we have seen group actions and some easy examples. Today, I will start with a field extension and then so-called the Galois group of that. And this will be the central theme in our course. So let us set up some notations. So I will usually denote L over K field extension. To each such field extension, I will associate a group. What that group will be called a Galois group. So when you have a field extension, that means K is a subfield of L. That means the bigger field L, you can think a vector space over K. So this L is a K vector space. Not only K vector space, it is because it has its own multiplication as a ring. So it is actually K algebra. This we saw in earlier lectures. It has a structure of K algebra. And usually when one says algebra, then there is a structure homomorphism. In this case, the structure homomorphism is this inclusion map, this natural inclusion with structure homomorphism. The natural inclusion K to L. This gives an algebra structure of K algebra structure of on L, on the field L. So therefore it makes sense to talk about K algebra endomorphisms, for example. Endomorphism from L to L. That means when one says K algebra endomorphism means, let us spell out what it means. First of all, it is a map from L to L. It is a K linear map, and also it is a ring homomorphism. That means it preserves the multiplication. That means it respects the multiplication, and obviously we have made our convention earlier that under ring homomorphism multiplicative identity goes to multiplicative identity. So that is still we are assuming that, and the set of all endomorphisms of the field L of the K algebra L, that I will denote end K algebra L. So this is just to remember that this is K algebra endomorphisms of L to L and K algebra. That means it's K linear. That means it's a vector space endomorphism, and in addition to that, it's a ring homomorphism. So if I write some from these, some notations will be obvious. NKL, this is just K linear map. These are just a vector space K linear endomorphisms of L to L. Only the vector space. That means it's K linear and it respects the addition. So therefore, this is a subset of this. It may be a proper subset. And when I say the automorphisms, K algebra L. This means they are not only endomorphisms, but they are bijective, and the inverses are also K algebra endomorphisms. So this is precisely all those sigma from endomorphisms such that sigma inverse is also endomorphism. The sigma is bijective and sigma inverse also is an K algebra endomorphism of L. So this is a subset of this, and more importantly, this is actually a group under composition. It's a group under composition. Because we have seen, if you have two algebra homomorphisms, their composition is also algebra homomorphism. Already inverse is algebra homomorphism, so under composition it's become a group. And let me also remind you, this is, if I write only odd KL, this should mean only a vector space automorphisms. So this is also subset here, and it may be proper. This also may be proper, and etc. So we are concentrating on this group. This group also I will keep denoting gal L over K. This is called a Galois group of L over K. Note that this group I have defined it for arbitrary field extension, and I still use the word Galois group because Galois is the first who started with studying such a group. Of course, Galois started studying such a group in a very particular situation, but the name continues to be for arbitrary field extension. So couple of remarks about this group. So first of all, note that this odd K algebra L, this is, if I take all bijective maps from L to L, SL, this is the notation I keep using, last time also used. This is the set of all bijective maps from L to L. Sigma from L to L, bijective. Sigma is bijective. This is called a symmetric group on the symbols L, the symmetric group of L. So this is actually a subgroup of this, because we know that the multiplication binary operation of this group is a composition, and the same is this is a group. This is a big symmetric group. This is very big group, but this is some elements among them. This is the Galois group, and we are going to study, we are going to do the following: this field extension and the group, that is odd K algebra L. This is gal. I should start using the notation gal L over K, because the more you use, the more you will get acquainted with. So this association from field extensions to groups, we are going to interplay between this. So we are going to extract information about field extension from this group, and also conversely from this group information about the field extension, and from field extension about this group, both ways, not just one way traffic, both ways. So that is what, therefore we have to understand this association more and more intimately. That is what we will do it. For example, is this group finite? If L over K is finite, is this group finite? If it is, what can be the order? And so on, such questions. So in the beginning, I will try to extract information only from the numerical invariants. For example, to a field extension, we have, because L is a K vector space, so we have this number dimension of L over K. This is the cardinality of a basis of L over K. This is also denoted by L over K, and this is also called a degree of the field extension, degree of L over K. And also we have group, so we have the order of that group. So the first question is what is the relation and some kind of relation. So this is what first I am going to do that. So the most important fact in this course will be the following, namely this automorphism group. So Gal L over K, the elements I will denote sigma, tau, etc. Elements are denoted by sigma, tau, rho, etc. They are automorphisms of the field extension L over K. This group operates, last time we saw group operation, this group operates on L in a very natural way, What is that natural way? It is so natural that very easy to write. So I want a map from Gal L over K cross L to L. This is my set X, L is the set X, and this is the group. And when we know that the group operates, means there is a map from G cross L to L which satisfies those two properties. So what is the map? Take any sigma and take any X element in L, and where can I map it? How do I get another element in L? That is sigma of X. Because sigma is what? Sigma is an automorphism of L. K algebra automorphism. This is a K algebra automorphism. So sigma operates on this. Now the whole Galois theory will center around studying this operation. What does that mean? That means studying the orbits, studying the stabilizers, and studying fixed points and so on. So as we progress in these lectures, I am going to make the vocabulary of group actions more and more intimater, and we supplement it by more and more examples. So before we go on to the numerical invariants, so some examples I should write in this view now. So first of all, if I look at the extension, the easy one, C over R, this field extension. So first of all, what is the degree? Dimension of C over R is 2. In fact, 1 and I is the basis. This is R basis. And definitely I know. So therefore, the degree, this is the degree. This is C over R. This degree is 2, cardinality of a basis. And what is the Galois group of C over R? This has definitely two elements I know. One is definitely identity is always a algebra homomorphism, identity of C. And then the other R algebra homomorphism is you want a R linear map of C, which also should preserve the multiplication, which also respect the multiplication, and obviously the sigma, which is a complex conjugation. This is complex conjugation. That is the map from C to C, which maps Z to Z bar. This is obviously R linear. R linear is obvious because Z is a real number if and only if Z bar is Z. So R is linear is obvious, and also it respects the multiplication. That means all that we need to check is Z times W, then the bar of that is same thing as Z bar W bar. This precisely means, these two together means, and obviously 1 goes to 1. This means that the sigma is indeed an R algebra automorphism of C. So this group definitely has two elements identity and sigma. And soon I am going to prove that these are the only two elements. So therefore, in this case Galois group is of order 2. And as we know, the studying groups of order 2 is very simple. Therefore, studying this extension will also be simple. That we also know. We have been studying complex numbers or real numbers very neatly. So this is one example. So another example is, suppose I take a finite field K, field with Q elements. K is a field with Q elements. So this is a finite field with 2 elements. Q elements, not 2, Q elements. So we have seen that Q has to be the power of P power m for some P, for some prime number P and some non-negative integer m. So therefore, this is a vector space over Z mod P, Kp is Z mod P in our notation. This is Z mod P. So this extension, this is the field extension, and we know what is the dimension. The dimension of Kq over Kp is nothing but m, this power m, that we have done in the last lecture. So this is a finite field extension of degree m. Now one should give some elements in the Galois group. So I want to give some elements which are automorphisms of Kq as Kp linear, right. So I am looking for maps which are Zp algebra homomorphism, which should preserve the multiplication, which should respect multiplication, which should respect addition, and also the scalar multiplication. Okay, but obviously in this case not much to check, so I will give you the map directly. So let us take the map x going to x power q. X power q, what is this map? We have seen that if I take raised to the power q, I get back x, because we know this kq cross, this group is cyclic or order is q minus 1. Therefore, when I raise arbitrary element to the power q minus 1, I get identity. So when I take one more, then you will get x. So this is just an identity map. But instead of this, if I would have taken x goes to x power p, let us check whether it is a algebra homomorphism. So what do you need to check? First of all, it is K linear. So this is K algebra homomorphism, that is very clear because of this x plus y power p is same thing as x power p plus y power p. That is because p is the characteristic. P is the characteristic of Kq. Characteristic of this field is p. Therefore, when I raise it respect addition, multiplication is no problem and linearity is also no problem. So it is actually Z algebra homomorphism, and it is automorphism because it's injective. It's a map from a field to somewhere, but a map from a field is always injective because it's a ring homomorphism also. So kernel has to be either 0 or whole. It cannot be whole because 1 goes to 1. Therefore, any endomorphism, any map from any algebra homomorphism from a field is always injective. So it's injective, and it is also bijective because of the cardinality argument, because it's a finite set injective map. Pigeonhole principle will say this map is bijective. So we have this map is very, very important. This map is called the Frobenius. The Frobenius was the first to consider this map. So I will keep this map as F Fp. So this is, so I will use the next page. So this map, so Fp, this is a map from, instead of q I will write p power m because then it's more visible. So k p power m to k p power m, this is obviously an element in the, this is Zp algebra homomorphism, algebra automorphism, that is what we have checked. This is called Frobenius automorphism. Okay, once you have one automorphism, if I compose with itself, that also should be an automorphism. So F compose F, Fp compose Fp. Let us see what this map is. This is in, this should be denoted Fp square. This is, what is this map? Where will it send x? The first Fp will send it to xp, x power p. This is the first Fp, and the next one again it will send to power pth power of this. So that is xp power p, which is xp square. And so we have definitely this Galois group, gal kp power m to kp power m, kp power m to kp. This Galois group, definitely we found some elements. One is obviously the identity map of kp power m to kp power m, then Fp, then Fp square, then I could take cube also. That will become the map x going to xp cube, and I can keep doing it to up to p power m. But when I do p power m, I will get back to identity map. So this one I can definitely go on till Fp power m minus 1, because Fp power m is the map x going to x power p power m, which is x. So therefore Fp power m is nothing but the identity map. So definitely I got m elements there, and I will show you that this is the, these are the only elements. So we would have computed the Galois group, and then we would have compared with its the degree. In this case, degree is m, and this, if I prove this equality, then the cardinality of this set is also obviously m, and therefore the degree will be equal to the order of the Galois group. All right. So that will be the, I will give more and more examples as we progress with more and more vocabulary. All right. So, and studying this, see, we are studying objects with their automorphisms. That means we are studying, for example, we could be studying groups G with automorphism group of G, that is odd G. Simply the notation will be this, they are automorphisms of G. Or before this we could have done sets, set X with the automorphisms of set, means just simply bijective maps, because there is no structure on the set other than the set. So that is all bijective maps from this. So this is odd X. So similarly you could have done it for ring R, ring, then ring automorphism. So I should write now odd ring. So the notation also becomes clearer, that we have to specify what structure preserving maps we want to study. So module, R modules, just say odd R, then module M, odd R M. That means all automorphisms of the module, means they are R linear maps, they are module homomorphisms and bijective module homomorphisms, they are automorphisms. Or you can do R algebras generally. So that will be odd R ALG and R algebra is B, then it is odd algebra B. So vector space is a special case of this. So that is odd K V, right? So this is odd K V. This is if R is K, and then this M is V. Then we write this. If this K is K algebra, then this is a field L, then that is our Galois group. So in all these are groups, and we are studying these objects with these groups. So now it is how big are these groups? The bigger the groups, the structure will be more complicated. Smaller the groups, the structure will be crude, because then you have not many possibilities to have automorphisms. So that is what. So I will prove the first connection, the numerical connection, that this theorem I will prove it when in the next half. So the theorem we want to prove is the following. Theorem, this is called Dedica and Artin. So L over K finite field extension, then the order of the Galois group, cardinality of the Galois group is less equal to the degree of the field extension. So we know that if you have a finite field extension, then the order of this group cannot be more than this. Already this will tell you for R over C, we have seen this is 2 and this is also 2, so equality should hold here. And then the group cannot be more. Similarly, for finite field extension of finite fields, already we have checked that this group contains so many elements, so equality should hold here. So this already proves that Galois group C over R is only two elements, identity and sigma, the complex conjugation. Similarly, Galois group of K p power m over Kp, this is already identity Fp and so on, Fp power m minus 1, because this can't have more elements, and once you check they are distinct, that's all. And in particular, this group is cyclic, no wonder, because it has only two elements, but even this group is cyclic because it is generated by the Frobenius. So this is cyclic, generated by Frobenius map, Frobenius automorphism. So we will come back and prove this theorem, and for this theorem we will use so-called Dedica and Kronecker theorem. We will see. My plan is to keep prerequisite as minimal as possible. Okay. So we will continue in the next half.